Okay, let's continue the discussion with this summary of CDR methods, the route through the carbon cycle that these methods employ, their technology readiness level, and their cost and global mitigation potential estimated for 2050, their key hazards and co-benefits, and the feasibility of monitoring, reporting, and verification of net CO2 removal. Some details there as well, so let me just run through the table. So here we are, the method, route of CDR, technology readiness level, cost in terms of dollars per ton of CO2 removed, the mitigation potential in terms of total gigaton CO2 they can remove per year, monitoring, reporting, and verification, examples of the hazards and co-benefits. DACS is direct air capture and carbon sequestration and storage. Excuse me there. So chemical capture via solid sorbent or liquid solvent, where concentrated CO2 stream is produced and the storage is done in the lithosphere. There are technology readiness level of 6 between 1 and 10, so they are beyond the halfway point. So pilot phase testing would have been done, some demonstration would have been done, and so on. Cost at scale $100 to $300 per ton. Mitigation potential varies largely from 5 to 40 gigaton CO2 per year. Monitoring, reporting, and verification. Capture, very high potential, not for reporting, and storage, high, yes. Increased energy use can lead to greenhouse gas emissions or competition for renewable energy. Increased water use with some options. So if people begin to see that DACS is working at a very high level, then they may think it's okay to continue to live in this carbon trap and keep emitting and keep taking it out. But this is a system with hysteresis, so putting it and taking it out is not the same as not putting it out at all. Water produced, so co-benefits, solid sorbent direct air capture designs only, so here humidity can also be captured and you can produce some water. Enhanced rock weathering, so this is geochemical capture via spreading of crushed silicate rocks on land or ocean. Storage in minerals or as bicarbonate. 3 to 4 technology readiness level, so still ways to go. 50 to 200 dollars per ton of CO2. I hope I didn't say it wrong. 2 to 4 gigaton CO2. MRV low and no. So this is very high and no. Storage low and no. So I will skip this because this is a bit complicated to interpret, but you can keep that in mind. So what are the hazards? Mining impacts, air quality impacts of rock dust when spreading on land, heavy metal contamination, especially nickel and chromium, and some rock types. So mining for these minerals and distributing them, transporting them, spreading them, etc. will have all sorts of hazards. Co-benefits can include reduced soil acidity and increased nutrient supply, which can enhance plant growth and soil carbon sequestration. So soil carbon is lost over centuries by human activity, especially agriculture, has to be restored, and increased soil carbon has very special benefits in terms of soil structure, how it can hold more water and retain nutrients, reduce erosion, increase crop yields, and so on and so forth, in addition to sequestering carbon. Ocean alkalinization. This is geochemical capture via adding alkaline materials to the ocean, such as silicate or carbonate rocks. I have brief discussions on these elsewhere. Storage in minerals or as bicarbonate. TRL 1 to 2, so very low. 40 to 260 dollars per ton of CO2. 1 to 100 gigaton CO2 per year. Increased seawater acidification. Saturation states may have local adverse impacts on marine biota. Possible release of nutritive or toxic elements and compounds may perturb marine ecosystems and will of course have mining impacts. So you have things like eutrophication possible here in addition to acidification. But reduced ocean acidification can benefit biodiversity, especially corals and crustaceans. So all the shell-forming animals like coccolithophores and so on. Ocean fertilization is where you put micronutrients, so biological capture via fertilization or enhanced upwelling. There are many ideas, but technology readiness is low. Cost is high compared to everything we have seen here, and the mitigation potential is low as well. And this will result in nutrient redistribution, enhanced oxygen consumption, and acidification in deeper waters, pumping more CO2. This could perturb marine ecosystems, could encourage toxic algae as well due to eutrophication. Fraction of removed CO2 reaching durable storage is uncertain due to metabolism, so it may enhance photosynthesis near the surface in the euphoric zone, but it's not guaranteed that what is photosynthesized will sink out of the system and actually sequester carbon. On the other hand, enhanced biological productivity which could increase fish catch. Coastal wetland blue carbon management, we have talked about this elsewhere as well as a natural climate solution. Biological capture via aquatic biomass like mangroves, kelp, subaquatic vegetations. Insufficient data here to say cost, and the mitigation potential is less than 1. But for a country like India with more than 7,200 kilometers of coastline, coastal wetlands can provide additional benefits, as we'll see here. Vulnerable to reversal through sea level rise, difficult to quantify CDR accurately. Additionality of CO2 uptake is hard to quantify. This can contribute to ecosystem-based adaptation, coastal protection, increased biodiversity, can reduce methane emissions, could benefit human nutrition, or be used to produce fertilizer for agriculture, to produce a methane-reducing feed additive to cattle, or as an industrial feedstock. So technically they can sequester 3 to 10 times more carbon than land forests, and they don't burn down, but there are all these issues to worry about as well. Finally, BECCS bioenergy with carbon capture and storage. So this is biological capture via plant growth, cropping, and forestry resources, organic waste, or purpose-grown crops. So concentrated CO2 and storage in lithosphere with cost at $5 to $6 per ton, so cheaper. Mitigation potential of technology readiness at 5 to 6, cost at $15 to $400 per ton, mitigation potential 0.5 to 11 gigaton CO2 per year. In terms of hazards, competition for land and water resources, food prices, food security, if based on purpose-grown biomass feedstock, loss of biodiversity, carbon stock, and soil fertility if from unsustainable biomass harvest, use of potentially contaminated biomass residues such as post-consumer food waste can pose air pollution risks. Co-benefits include bioenergy, so bioelectricity, biofuel, biogas, which can displace fossil fuels and enhance fuel security. Reduction in air pollution when engineered BECCS facilities displace in-field biomass burning. Utilization of residues provides additional income and can improve crop growth and health. Purpose-grown biomass crops can enhance biodiversity, soil health, water quality, and also sequester additional soil carbon. Afforestation, reforestation, which has been put into the nationally determined contribution promises under Paris Agreement by many countries, including India, for example. This is biological capture via trees. As we said, additional sequestration has to be quantified and reported. Technological readiness level is very high, already being used in many places, and there is some natural afforestation that's been reported as well, especially over India and China. And the cost can be $0 to $240 per ton. Sequestration potential is 0.5 to 10 gigaton per CO2 per year. Of course, there is reversal of CDR through wildfire, disease, pests. With climate change, they get worse. Reduced catchment water yield because more is taken up by the afforested area or reforestation area. Lower groundwater level if species and biome are inappropriate, so one has to carefully choose what is appropriate to be planted. Finite carbon carrying capacity of land. Capacity may be reduced under climate change. With warming, soil heterotrophic respiration goes up. there are issues of whether plants will continue to capture more CO2, but on the other hand, you also have CO2 fertilization effects when you increase forest cover. Enhanced employment and local livelihoods, improved biodiversity, improved renewable wood products provisions, soil carbon and nutrient cycling, possibly less pressure on primary forests. So the old growth forests compared to the new forests can maybe protect old forests or primary forests. Biochar, biological capture via cropping and forestry residues, organic wastes or purpose-grown crops. Technology readiness level is reasonably high at 6 to 7 and cost is reasonable at 10 to 345 ton per CO2. Sequestration potential is low compared to others at 0.3 to 6.6 gigaton CO2 per year. Hazards include particulate and greenhouse gas emissions from biochar production, biodiversity and carbon stock loss if from unsustainable biomass harvest. On the other hand, increased crop yields are possible, reduced non-CO2 emissions from soil, and resilience to drought, because increased soil carbon always increases soil moisture holding capacity, soil moisture residual residence time, groundwater recharge, and resilience to drought. Soil carbon sequestration almost sounds like a no-brainer, but what are the costs and hazards? Biological capture via various agricultural practices and pasture management, so agroforestry, no tillage, organic manures, and grazing management, etc. are key. Technology readiness is high at 8 to 9, like afforestation and reforestation. Cost can be negative in terms of providing co-benefits, $200 per ton, and sequestration potential is 0.6 to 9.3. In terms of a life cycle analysis, the co-benefits here are not always counted in terms of the costs, for example. So hazards: increased nitrous oxide emissions due to higher levels of organic nitrogen in soil. Nitrous oxide is a very powerful greenhouse gas. Finite capacity of soil to protect organic matter, so with temperature increase this can be a problem. Capacity may be reduced under climate change, which is what I just said. Improved soil quality can be a co-benefit with resilience and agricultural productivity going up. Next one is peatland and wetland restoration. Many of these count as nature-based or natural climate solutions as well, but here we are looking at them as CDRs. So here biological capture via re-wetting and revegetation with high technology readiness level, and cost is not estimated because of insufficient data, and sequestration potential is small, but there are many co-benefits in terms of migratory birds, people using them for hunting and tourism, ecotourism, and so on and so forth. Hazards, of course, are increased methane emissions. Methane, again, is a very powerful greenhouse gas, about 25 times as powerful as CO2, but N2O is almost 200 times as powerful as CO2. Co-benefits include increased productivity of fisheries, improved biodiversity, soil carbon, and nutrient cycling. Agroforestry, which I mentioned, biological capture via trees. In poor countries, this is very critical because other than non-rainy season income, rain-fed agriculture tends to be only during the rainy season, causing other socio-economic problems like farmers leaving the villages to go work as migrant laborers. There are other problems associated with that on family life quality, standards of living, etc. But agroforestry has lots of other benefits. High technology readiness level has been practiced for a long time, actually. Industrial agriculture took it away, but insufficient data to estimate costs, and the sequestration potential is 0.3 to 9.4. Hazards, of course, trade-offs with agricultural crop production, and actually understanding the mental model of farmers to see why they don't implement agroforestry even when benefits may be obvious has to be figured out. In terms of co-benefits, again, enhanced employment and local livelihoods, variety of products, improved soil quality, more resilient systems, drought resilience, groundwater recharge, soil moisture residence time, persistence, etc. Durable harvested wood products, biological capture via trees. So this is growing trees to lock them up into wood products, including buildings. So I have podcasts under drawdown in coming attractions to see how wood can actually be used to build multi-storied buildings. We almost always think that wood cannot be used to build high rises, but actually that's not true. Technology readiness is high, data is insufficient for cost estimation. The sequestration potential is small, but just the aesthetics of having wood buildings may offer lots of other well-being opportunities. Hazards come in terms of increased fertilizer use, and introduced species could reduce biodiversity and increase eutrophication, and of course there is fire risk every time you use wood. Co-benefits include reduced ecological toxicity, improved human health and well-being, and reduced duration of construction compared with alternative building materials. Okay, recycling will be easier compared to concrete, steel, and so on. Finally, improved forest management, another natural climate solution where you are doing biological capture via trees. Technological readiness is very high. So there is restoration, afforestation, reforestation, and forest management. Reduced deforestation and degradation, for example. Technology readiness obviously high, data insufficient for estimating costs. Mitigation potential can be critical in terms of other co-benefits, but the hazards include increased fertilizer use and introduced species, which can reduce biodiversity and increase eutrophication. But co-benefits include improved productivity, enhanced employment, and local livelihoods, and this can enhance biodiversity as well. Okay, for each method's route, the ultimate form of carbon storage is color-coded to match the carbon capture pools in figure 1.2, which I didn't point out before, but you can go back and look at the report. They use the IPCC's methodology for biochar monitoring, reporting, and verification. Lots of details there that I haven't gone into. Data for wood in construction is taken from some source. There are many such details that you can look up. So let me leave this podcast here and then come back and continue with some more points from the report State of CDR. Okay, very nice report, lots of details, lots of useful information. I'm doing it as usual briefly and at an introductory level, but the report and the incredibly long list of references will be very useful if you're interested in pursuing this further. Okay.